I'm Ed Armstrong from the NASA Jet Propulsion Laboratory in the California Institute of Technology in Pasadena, California. And I'm going to talk to you today about optimizing data and services in the cloud for user exploitation. Listed with me is my family of collaborators from both JPLers and various contracting companies that support us. So cloud computing is really a new frontier. This is new paradigms for data storage and access, and most importantly, computing. And really it's about computing next to the data is what we are discussing about in this presentation, focusing on various Amazon Web Services. So there's a large ecosystem of services, and we're using some of the components of those services to perform these cloud computations. For cloud computing, the advantages are the near unlimited and scalable compute that uses this family of AWS services, but of course there's certainly limitations and barriers. Number one, there's a learning curve and training necessary for the effective use of these services and for cloud computing in general. And also there's a cost component where cost management is critical. Of course, this is not free. You need to pay for these services. And the services ecosystem itself that include things like EC2, that's Elastic Cloud Compute, Lambda, SageMaker, there's a really broad spectrum of services. This is a quite confusing and daunting list of services of which one to choose and how to implement and how to manage. And lastly, the third-party support that we may be used to may be lacking or really requiring new cloud-friendly ecosystems such as the Pangeo or Coiled. Those are just a few examples. And of course, PODAC data and services are now 100% hosted in the NASA Earth Data Cloud in AWS West. And see the presentations by Wen Hao Lee and Suresh Vanan for more details on this. So this little schematic shows the NASA transition, Earth data transition to the cloud, where the cloud data and all the tools and services now live in what is known as the NASA Earth Data Cloud in AWS West. And the user can interact with these data and these services while being directly in the cloud in a most efficient manner. That's the scientific analysis in the cloud. But I do want to point out that, of course, you can still download and compute locally. That is still a valid option for users. This talk is going to be broken into three components. The first two components are really focused on cloud computing on AWS, and I've assembled a few use cases of using the different services to perform various tasks. The actual science computing is kind of light, maybe a little bit trite, but what we're really trying to do here is demonstrate and show you some examples that can be extended in the future to actually really do some heavy scientific computing. So the first one is scientific computing using the AWS Lambda. This is a scalable and serverless compute service, and we're going to be performing that on the Muir SST time series. And what we want to do is build a workflow so we can perform a 1-year daily average, with the idea that we can extend this to do cross comparisons to multiple SST data sets. The metrics we're going to be looking at are both our performance, scalability, efficiency, and cost. The second use case, we want to demonstrate scientific computing using EC2 and Dask. So a Dask is a Python library to perform parallel computing, and we're going to be using this to perform data downscaling again on the same Muir time series, and looking at metrics of performance, efficiency, and cost. The third topic I want to cover is a little bit tangential and a little bit more of a fun fact, but this is about cloud optimizing for the HDF5 container by leveraging internal file metadata optimization strategies. This is to increase the read performance for in-cloud read access. And it's important for many legacy single-file HDF5 files in Earth Science. Of course, we're in the NetCDF4 world in GRIST. And NetCDF4 is actually an HDF5, but we are currently investigating the ramifications for NetCDF4 files. So really what the performance or the application I'm going to talk about refers to HDF5 files. But I think you'll find it quite interesting. Okay, so the first use case again is the scientific computing using AWS Lambda. So AWS Lambda, again, is a serverless computing service that's event-driven, and it's really designed for computations across large data volumes that need to scale up rapidly, and best for discrete tasks. It certainly has some limitations. The Lambda compute nodes only have a 15-minute execution limit. There's a timeout after that. They only have access to 10 gigabytes of temporary storage. There can only be 1,000 concurrent executions. And unfortunately, these Lambda nodes cannot talk to each other, so you can't pass the results from one node to another node as you're going through your workflow. Again, the use case that we're going to be performing using this service is we're going to use the AWS Lambda and the EC2, which is the Elastic Cloud Compute. That's the common service that I think most people who have dabbled in cloud computing are familiar with, and other related services to compute a daily global mean of the Mir and the Mir25 SST time series. Okay, so I'm going to just show you the workflow of this particular example. And the first part of the workflow, the workflow does run in a Jupyter notebook. It can either be run locally or in the cloud. We're going to start off, we're going to say we're going to be running it locally. And essentially what this notebook does is query for a list of data granules through the NASA Earth data search interface that queries for granules in the common metadata repository. We're going to get a list of those granules, loop through each of them, and invoke the Lambda service to run on each of them, and read the outputs and plot the global mean over the time, and then do a little bit of cleanup. So here we're running locally. Of course, the data is in the NASA Earth Data Cloud, and we need our NASA Earth Data login credentials to be able to pass those to actually read the data in the NASA Earth Data Cloud. So here in this case, the first step, of course, is to query for the list of granules, invoke the Lambda for each granule that we find in AWS, and then do our various performance on them. That's the daily average, and then bringing those results back locally, storing them, and eventually plotting them. So what we really want to do, in a more efficient manner, is actually to have this workbook running in the AWS cloud as an EC2. So this will both improve speed and access, and so this is what this particular diagram shows. Here we are in the cloud, so it's encapsulated by the rectangle that shows, the blue rectangle that shows we're in the US West part of AWS, and we're right next to the NASA Earth Data Cloud data, and we can perform this workflow as we would locally, but it'll run much more efficiently. So we first query for the list of granules, and we evoked the Lambda on each of those granules we find, and we do that for each as we go through the loop. We read the information, calculate the global mean for that granule, and then store the result of that calculation in an S3 bucket as a netcdf file. So that's the main part of the workflow, and then once we have it done, we can go back and extract the results of those averages that are stored in netcdf files on S3 and do the plotting. So the general setup requires, of course, this is Lambda. It requires that your code be packaged as a Docker container usually, or a zip file, and some other small steps include things like setting up a role for Lambda to run as. We call that the IMA role. There has to be a parameter store that allows you to hold the Earth Data login credentials, and the Elastic cache registry for the Docker container if you do use the Docker to deploy to Lambda, and access to an S3 bucket to save the results. So the Jupyter Notebook is the one that invokes the Lambda function and plots the results, and this all runs in an EC2. That is, the compute part of this workflow, or it's kind of like the it's necessary to run the Jupyter Notebook. So again, this is a schematic of the deployment architecture that shows where on the left-hand side we're in AWS US West, where we have instantiated an EC2 that runs the Jupyter Notebook, and these are and below that in the purple rectangle are all the different services we're invoking in Amazon West, including the Lambda and the S3 and the IMA. And we're pulling, certainly there's a Podak GitHub site where we're pulling, and the Jupyter Notebook, that's under configuration management. And there's also another service called Terraform that's actually a software ecosystem, so basically a deployment package that allows you to deploy and manage things like the AWS Lambda service. So that's all contained in these Terraform and the configuration files that Terraform needs. All right, so this is just basically showing the workflow and the schematics. What is the actual result, and what do some of the performance metrics look like? So in this case, this is just a one-year time series of Muir starting in 2022. And this shows a plot of the global mean sea surface temperature for both the two products, the 1 kilometer and the Muir quarter degree product. And to do this single year time series on AWS Lambda and all the other related services, including instantiating EC2, costs 72 cents. And if you were to scale this up for 10 years, that would be $7.22. And Muir is over nearly 20 years now, so if you were to double that, you'd be closer to $15. AWS actually provides a calculator to estimate the cost, so you can keep tabs on this. We do have some ongoing work here. As I said in the beginning, this example is not really, it's somewhat trivial. We're not actually doing really any hardcore science here, but we do want to extend this workflow to be able to run on multiple gridded SSD data sets, to do pixel by pixel comparisons, do things like cross correlation. And to do that, of course, as I mentioned, these Lambda nodes do not talk to each other, so we're exploring using things like AWS DynamoDB or Glue or step functions to be able to store these interim results, the sums of squares, the number of samples, to be able to perform these higher order statistics. And the goal here is to develop an end-to-end workflow for user exploitation across for multiple SSD data sets to do cross comparisons and correlations at selectable spatial and temporal scales. So we're working on this. See us at the Ocean Sciences meeting in 2024 for updated progress. So that's use case one. On the second one, we're going to be looking at scientific computing using EC2 and Dask. So just a quick review on EC2. This is the virtual machine that people typically use to do scientific computing in AWS, where you can install software, run code, create files, etc. And they're actually created with varying numbers of processors and processor types and RAM, depending on your need. And of course, the cost model for each one of those combinations changes. So some of them are cheaper than others. Others are more expensive, as we'll see. We're using Dask here to do the parallel computing. This is a Python package providing options for parallelizing code and doing the computations. And it's nicely tied to the EC2 instances of varying sizes, so we can speed up computations. Okay, so here we have a workflow. We're instantiating an EC2. We're using, of course, our Earth data logins to gain access to data that's on the NASA Earth Data Cloud. Again, this is Muir data, and we're going to be using Dask to analyze the data using other Python libraries such as Xarray and NumPy. And what we want to do here is downscale the 1 kilometer Muir data to 100 kilometers using a generalized parallel compute approach using Dask. So this is almost a common use case when working with gridded data sets, where you say have gridded data sets at different resolutions and you want to put them on a common grid for comparison purposes. We've developed a Jupyter Notebook that demonstrates this workflow. So some of the performance tests we are performing here is we're determining the cost and the speed of downscaling, say 10, 100, 1,000 files, or even the entire time series, using different categories of EC2s. And if I jump to the notebook here, this will show now some of these different categories of EC2s that I just want to briefly make you aware of. This is the actual notebook that's been developed to do the computations. And down here there's a little description of the various different EC2 instances you can start up and execute and of course pay for. So the first one only is a general purpose. It only has two CPUs, so not terribly beneficial for doing parallel computing. But some of these other ones, the compute optimized and the memory optimized, have up to 128 or 48 workers. And so those are well suited for, of course, doing parallel operations. The compute optimized are ideal for the compute-bound applications, that benefit high-performance processors, while the memory optimized are designed to deliver faster performance for workloads that process large data sets in memory. And as we'll see, all these have different ramifications on their performance depending on how you use them and how they actually work on this particular operation. There's also the accelerated compute that has hardware acceleration options, and actually is the most expensive. You'll see in this category here is the cost. That's the most expensive. Accelerated computing, of course, the general purpose is the cheapest. And the compute optimized and the memory optimized fall somewhere in between. These are typical prices on a Linux on-demand hourly rate. So let me pop back to the presentation. And 1 second here. So here we see some of the cost results for the various different EC2 instantiations. On the right-hand side, we see the cost for downscaling for 100 files, 1,000 files, and the entire record. Both the memory optimized and the small general purpose have the lowest cost. Of course, we'll see speed is a factor here. So even though cost is very small, or for the small general purpose EC2, that's probably not the way you want to go if you're interested in speed, as we'll see on the next diagram. But of course, what this intends to demonstrate is also that the accelerated computing EC2 does not seem to do is actually the most costly. And so that's an important consideration, right? When you're designing these workflows, the point here is like which EC2 is the most efficient cost-wise, the least amount of money spent on for the performance of doing the downscaling. So that's cost, and now we look at speed. So the key, I guess, one of the key points here is if we look on the upper right is the computation time in minutes. There's a huge difference if you choose the parallel route versus the sequential route. So if it's just a typical classical sequential route where you're doing the downscaling one by one, that's something you would probably do with the bare bones EC2. It's going to take you hours and hours and hours to do 1,000 files. But if you use the parallel route, say with something on the order of 48 workers, you're down to 15 minutes. So that's a huge difference. The other diagram on the lower right shows again some comparisons in time for the different configurations, EC2 configurations. The point here is that the accelerated computing instance, it has the really high price per hour, but is actually slower than some of the other task configuration instances that were much cheaper, say the computing and the memory optimized configurations, which were all kind of pretty similar, kind of like wound up in this area right here. So that's an important, I guess, piece of information. A little caveat there that really the cloud optimized and the memory optimized, actually the family of memory optimized, seem to be the best bang for the buck in this case, with regards to cost as well as the number of workers and the performance that you can get out of them. So, like in a nutshell, we've done a little trade study here, and we do have some idea how EC2 and Dask perform on this simple task. There's some ongoing work. We're looking at a package called Coiled, which is a commercial Dask management system that allows you to just spin up and scale down on an as-needed basis. Of course, Coiled is it's a commercial company, so you have to pay for it. It's a software as a service. But there is a free trial available that we're leveraging, and we're seeing some very interesting and positive results using this coiled service. We wanted to actually apply it to do something a little bit more scientifically robust, and we're looking at applying it to do an EOF analysis on this same Muir time series of bringing both DASK and coiled into the mix for this, and we'll report on that at a future meeting. We're also usually utilizing X-Array's built-in functions for cookbook tutorials as they naturally play well with DASK. And the cookbook, we'll be adding these specific tutorials to the cookbook. Actually, one already is, the one on the AWS Lambda. But yeah, the cookbook is certainly the foundation for the user community to be able to learn about these various techniques, including simple and more advanced scientific computing techniques in the AWS cloud. So here's a list of some of the resources. The first bullets there are actually the links to the documentation and the location of the code for both the AWS Lambda example and the AWS and DASK example on our PODAC GitHub site, and various other links. So have a look at those and certainly get back to us with any questions. So my last topic that I wanted to talk about was HDF5 cloud optimization. This was inspired by some recent work by Alex Jelinek from the HDF5 group, who performed some initial explorations on this HDF5 optimization for S3 HTTPS cloud access. The key here is that the default HDF file data and metadata model is not well suited for cloud operations. There's actually a feature that you can leverage called page aggregation, where you can optimize the page size to improve the cloud read access in conjunction with read buffering. And he's developed a program suite to test this that can be packaged up into a Docker container, and essentially it navigates and prints out all the storage locations for every single data set and every single chunk in that data set that's contained in the file. So a little bit of stepping back a little bit, we need to present this as, why do legacy HDF5 granules perform poorly in the cloud? Well, really, HDF5 was built in the pre-cloud era when reads to local disk or even network file systems was very cheap and fast, on the order of milliseconds. In that particular era, the number of read operations was not particularly a high concern, but now we're in the cloud and the paradigm is flipped in this cloud object store with its key value interface, where the reads actually become long and expensive, and therefore we need to the read size quantity should be optimized as best as possible to minimize the number of reads. Now, the HDF5 library and H5Py actually have this feature, or read the internal metadata and raw metadata in fixed page sizes that are not optimized for the cloud in the default mode. And as a further compromise, nearly the entire internal metadata contents must be read before any file I/O operation can be done. So when I'm talking about the file metadata in the HDF5 container, I'm not talking about things like the global attributes or that contain things like the CF attributes, but this is actually internal file metadata, part of the HDF5 data and metadata model that tells the HDF5 reader where to go in the file, the byte offset to read or write a variable or data set and its chunks and the chunks of that variable. And one of the key points is that in the legacy world, these small snippets of metadata were really scattered everywhere in the file and were of very small size. And there was some reasons for doing that in the past, where read access and parallel operations on local files was key. But this does not work well in the cloud. In fact, it does not work at all. Well, it does work in the cloud, but as you see, it's extremely slow and expensive. Here's an example of a non-optimized HDF file and its metadata. This is from a ISAT-2 granule. So ISAT-2 is a LiDAR mission, a NASA LiDAR mission. And this is a snippet from the H5 stat command that shows that documents the metadata and the page size of the metadata and the actual total size of the metadata. So the first purple box shows the file page size. In the default mode, the metadata are written in these small 4K byte snippets. But the total size is actually over 4 megabytes. And so you can imagine there's these little 4K snippets that are scattered like randomly all over the file. And each time you perform a file operation and seek out a data set or a chunk of a data set, you need to read that metadata that tells you where to go. Now that little 4K snippet might be at the beginning of the file. You might get lucky, or you might get really unlucky at the end of the file. But you need to continuously read this metadata until you find out exactly where to go. So this is the issue with the default HDF5 model, is that the metadata page size is too small and it's scattered all over the file. So here's where we want to leverage page aggregation and do read buffering. So if we implement this page option at the creation, either or after the fact using the H5 repack, we can use a size, or we can create the file with a size so a single read will get nearly all the internal metadata contents. And we want to use a size that's in the region that's optimized for S3 range access. And this is about on the order of 10 to 16 megabytes as recommended by AWS. And we use that size in conjunction with the HDF5 library buffer caching capability that must be on the same order or multiples of 2 of the page size. And you'll see how this works in a second. This paradigm of having a single collection or entity of the file metadata that contains all the byte offsets is really simple and similar in principle to the architecture of native cloud formats like ZAR or H5 files optimized, or using the Kerchunk package, where the file metadata is all externalized in a little lightweight JSON file that you can easily read, and then you can figure out where to go in the actual data to fetch your data. So this is an example if we use the H5 repack command, and you see an example of the repack command right there, where we take that same granule and now we repackage the internal metadata contents to something on or the page size to something on the order of the original file metadata. So you can see we've created a page size of about 4 megabytes. There in the first red box, and so it's just smaller than the actual file metadata size, which is a little bit larger. And so now we have all the internal metadata in a page size that's appropriate for one read, where we can read it and get nearly all the metadata. And so we'll just need to read that file metadata once, and we'll know exactly where to go in the file to read the information of interest. So we designed a little performance setup for various HDF5 test setups. So we really only report on the ISAT granule, but we've used the H5 repack on these granule and optimized the internal file metadata for each of them using the H5 repack command. And then we use this nice Docker container test kit designed by Alex that navigates the entire file and prints out the storage locations of all the byte offsets. And we time that. So that is the performance to time that particular run of the program as it navigates the entire ISAT file. So what does that look like now for a optimized and a non-optimized ISAT2 file that's been stored in AWS West S3 bucket? So this particular file is over 1 gigabytes in size. It has over 1,000 data sets, 171 groups, and again the file metadata is on the order of 4 megabytes. So the results here show on the left hand side are the file page sizes. The original was 4 kilobytes, right? So that's reported there. And we don't implement any read buffering size because there's no page aggregation implemented. To actually run that program and then traverse the entire file took over 4 minutes. But if we implement the paged aggregation and we set the appropriate read buffer size, we're down to the order of 3 seconds. So a tremendous difference. When you implement this page strategy, the actual size of the file does grow somewhat, and in this case it was less than 1%. So we see here by implementing this file page aggregation strategy and setting the appropriate read buffer size hand in hand, they have to be multiples of each other. We're really down, we're down to 3 seconds, and that's really at the order if you were to have this file on a local file system. So, kind of typically the way we used to work back in the day were things like access time access wasn't really of an issue. So this is the same file here, and as you see here, locally, if we just have the file locally, the time to runtime for this program is 2.5 seconds. If we implement some page aggregation, it's really the same. It doesn't really have much of an effect at all. But the key here is that reading the file locally, like once we're in the cloud, we can read the file on the order of the same time as if the file was locally. And this result, it actually has real-world implications and has been implemented as part of the NISAR science data system, because we've seen now the benefit is that we can create an HDF5 file and be able to access it and use it as if we were using it locally, which is how we would use science data in the past. Of course, this is the HDF5, and we're in the NetCDF4 world in GRIST. A NetCDF4 file is HDF5, but the NetCDF API and library are different. How the NetCDF library, how it uses, or if it can even implement the page aggregation is really unknown at this point. Of course, H5 repack can be used after the fact on any HDF5, including NetCDF. So we're looking at doing some exploratory research in this area. We have shown some modest improvement for GRIST NetCDF4 granules using these techniques, but we really need to take a little deeper dive. Our particular granules are not overly large or complex with regards to the number of variables or groups, but there still might be some modest improvements or techniques we could adapt from this methodology that'll improve the access of these granules in the cloud. So see us at the Ocean Sciences meeting in February 2024 for more progress on this topic. So to wrap up, cloud computing, it's a new ecosystem for scientific computing. It does require new knowledge, skills, techniques, and understanding of the entire services suite. We presented 2 advanced use cases of cloud computing using AWS Lambda and the EC2/Dask. For the data producers, the HDF5 internal metadata aggregation is critical to improve the cloud file I/O, but we don't really know the exact NetCDF4 impact. So, its impact on the GRIST and the GRIST products is really unknown at this moment. More investigation is underway. And PODEC is really here to help you on your cloud journey. So we will continue to publish more tutorials and develop experimental workflows, hold workshops and hackathons, and just try to provide general support to exploit the cloud. And of course, see the talks by Suresh Vanan and Wenhao that provide some of the more detail on the various different services, cloud-based services that we have developed and made available to the user community so far. So I'll wrap it up there. Thank you very much for your attention.